now pleased to welcome to the stage Dr. Deepak Raghavan, who will tell us more about our panelists and introduce the program. And as Deepak joins us on stage, I wanted to share with you a few observations about him as a fellow Rotarian and member of our club. I first met Deepak over 25 years ago, and he has done unique things in this organization and in this community that many of you may not be aware of. Over 25 years ago, Deepak was co-founder of Manhattan Associates, which has become one of the most successful technology companies, not just in Atlanta, in the world. The company was taken public. Today it has a $15 billion market cap. It has been one of our most successful businesses in the supply chain area. Now, most of you, after taking a company public that has $1 billion valuation, would probably go off and buy a deserted island and retire there for the rest of your lives. But not Deepak Raghavan. Deepak Raghavan went off to get his PhD in astronomy and astrophysics. He studied environments around sun-like stars to learn more about potential habitats for life in the universe, leading to this program today. He published his thesis results in the Astrophysical Journal in 2010. It's the most comprehensive assessment of companion stars to sun-like stars and has over 1,400 citations to date. Now, in our community, Deepak has also given back. He's very involved, along with his family, in a number of worthy causes. They've created their own foundation. They focus on education, animal conservation, and children's health care. And today, Deepak is an active board member at the Smithsonian Astrophysiological Observatory, the Atlanta Police Foundation, and Zoo Atlanta. And a little-known fact about Deepak is also that he has run a half or full marathon in every state in the United States. So he is a well-run person. Let's give Deepak a hand, please.
Thank you, President John. We all know John's commitment to Atlanta and to Georgia. We know of his championing of entrepreneurs, and we know that he can make important connections and introductions. I got to see all that firsthand when we moved the company to Atlanta in 1995, when Manhattan Associates was just 5 years old as a company. Thank you for that, John. He was our external counsel and a key advisor during our pivotal time, pre-IPO growth time. Now it's my pleasure, as I welcome Dr. Lisa Cooley and Dr. Randall Smith to the stage, to introduce our speakers for today. Professor Lisa Cooley was selected to lead the Center for Astrophysics in 2022, and she has hit the ground running with her bold and aspirational vision, her strategic priorities, and creating an organizational structure that's going to enable this organization to reach new heights. The Center for Astrophysics is the prestigious and largest astrophysics group in the world, and it brings together two of our iconic institutions, Harvard University and the Smithsonian. It's a joint collaboration between those two. At the CFA, astrophysicists are searching for answers to some of our most basic questions. Are we alone? How did the universe form? What is its ultimate fate? Hard questions that very smart people are working on. In search of these answers, they push the very boundaries of science and engineering, and we'll hope to hear about, you'll get a snippet of that today, and if you're interested, there's more later if you get in touch with us. As their advisory board chair, I am pleased to have a front row seat at their exciting discoveries. Lisa earned her PhD at the Australian National University for her studies connecting supermassive black holes at the center of galaxies with the process of star formation in the galaxy and other stellar properties across the galaxy. These supermassive black holes at the center of galaxies are massive, as the name suggests. They weigh 4 millions to billions of times the sun's mass. And yet, in scale and mass of the galaxy, they are small, but they still influence processes of stars in the galaxies, and that's what she studied. Dr. Cooley has been recognized worldwide for her research contributions and her leadership, and has received many inductations into organizations and awards. I'll just point out one. She's a winner of the James Craig Watson Medal from the U.S. National Academy of Sciences. And Dr. Cooley also has an interesting Rotary story that she will share when she makes her introductory remarks. Welcome, Lisa Cooley. Hold on a second. Our other speaker today is Dr. Randall Smith, Associate Director of Science at the Center for Astrophysics. He's an expert in high-energy astrophysics. You might all be wondering, what is high-energy astrophysics? I'll give you 3 definitions of it from my standpoint. Number 1, everybody that I've seen in his team, and everybody, in fact, that I've seen at the Center for Astrophysics is a high-energy person. So I think it qualifies on that metric. It is also the study of high-energy processes in the universe in places like in the vicinity of black holes, on the surface of neutron stars, and very different and foreign environments from what we have here, where electrons with very high energy are interacting with plasma material. And he does this primarily by studying high-energy photons. So we have light as the electromagnetic spectrum, and on the high end of that energy spectrum, we have X-rays. And most of his career, Dr. Smith has worked with NASA on various space missions studying X-ray observatories. He has been to all 7 continents. I have not done that, John. I've only been to the 50 states. And he has done that both for science as well as for his efforts in teaching, teaching astronomy capacity building workshops. And he's working on a book on secret science, and he's a juggler. In addition to juggling all his scientific priorities, he can also juggle, which is a good skill to have. I now welcome, let's recognize Dr. Smith as well. I now welcome Dr. Cooley to share some introductory remarks, after which we'll get to a fireside chat.
Thank you, Deepak. And before I start, I just want to thank a few people, John Yates in particular, thank you very much, and the Rotary Club of Atlanta for having us here today. I hope you enjoy the event. We're going to be sharing some exciting discussions and discoveries with you today. I also want to thank Deepak. Deepak is a wonderful board chair. We're tremendously excited to have him leading our advisory board, and I want to thank Deepak for helping host us here today. And also thank you for Jennifer Doran, that's how to pronounce the last name? Thank you, for helping us set up this event as well. Thank you very much. And also, I just wanted to recognise that we've got a new board member, Mark Pirung, who is here today as well. So thank you, Mark, for joining us today. All right, so I have a story for you, and it's about how I got into astronomy. Lots of people ask me how I got into astronomy. Well, when I was in high school, I was a junior, and my physics teacher loved astronomy. And I told him I was interested in astronomy. He started feeding me all sorts of books and papers and articles about black holes and wormholes. And he had his own telescope. And he brought us out, our whole class, out on an astronomy camp where we got to look through his telescope. We tracked the moons of Jupiter. We looked at Saturn. We looked at how the constellations moved across the sky. We made our own sundials and tested them. Mine wasn't that good, but it was a wonderful camp. And so that really got me interested in astronomy. The same year, Rotary in Australia was sponsoring a national science summer school. So they were sponsoring kids to go to this science summer school, and they were selecting the kids who would go. So this was an intense selection process. So I went to my local Rotary, Modbury Rotary Club, I applied, and then there was 2 sets of interviews, one with the Modbury Rotary Club, one with the District Rotary Club, and I was tremendously excited to be selected by the clubs. And they asked me a really hard question. It was, how would you solve the Earth's energy problems with astrophysics? And so I'm delighted that they selected me. I went to Canberra where they had the Science Summer School, and I was put in a group called Galileo. And the Galileo group got to go up to the Mount Stromlo Observatory where astronomers talked to us. Now, I could not believe that there were people there who were astronomers who were paid to be paid to be astronomers. I would just remember thinking, I can't believe they pay people to do astronomy. And that was it for me, that I just decided, okay, I want to be an astronomer, I want to go to Mount Stromlo, and so that's where I ended up doing my PhD. So I just want to thank Rotary everywhere because they gave me a great start. Okay, so now I'm going to tell you a little bit about the Centre for Astrophysics. As Deepak mentioned, we are the convergence of the Smithsonian Astrophysical Observatory and the Harvard Astrophysical Observatory. So the two observatories combined together about 50 years ago. Smithsonian Astrophysical Observatory was primarily a solar observatory. They were based in Washington, D.C., but they had solar telescopes around the world connected up through a network. At the same time, the Harvard College Observatory was a stellar observatory, so they were observing stars and things more further out in our own Milky Way that we didn't know were in our Milky Way. They were also looking at other galaxies at the time. And so the two organisations were complementary. They both had stellar expertise, and the Smithsonian Astrophysical Observatory brought the solar expertise. They'd already been working together on space programs. So they actually, decades earlier, so 6 decades ago now, they had been working together on some of the first astronomy-based space missions. And so they'd already been collaborating. And so it seemed a natural step when they decided to move the Smithsonian Astrophysical Observatory to Boston to join with the Harvard College Observatory to make it the biggest astronomical organisation in the world, and to combine the solar expertise with the stellar expertise and the telescope together. Now we have 850 people in the organisation. We have 4 buildings in Cambridge, Burlington and Arlington, if you're familiar with the Boston area. And this includes a large engineering program. We have 60 engineers, and we have a large program management office. And with that team, we're able to build ground-based telescope technology as well as space technology. So we don't just make the discoveries, we build the technology that we need to make those discoveries. And we do this in many different areas. We do it in radio, optical, infrared, as well as X-rays that Randall's going to be talking about. We also operate telescopes around the world, including the submillimeter array in Hawaii, as well as the multiple mirror telescope in Arizona, the Greenland telescope, and we also operate a gamma ray telescope, and that's based in Arizona. These are operated on behalf of the whole astronomical community, and we also are a partner in the Magellan telescopes in Chile. Okay, you might remember this in the news, this orange donut here. This is an image of the black hole in the centre of our Milky Way, and this was founded and led by our institute. And in particular, one of our astronomers, Shep Doleman, this was his idea over a decade ago, and it takes a while to develop an idea and then to be able to take the data, a large amount of data, analyse the data, and then to make the image of the black hole. Now the black circle in the middle is the black hole. It wouldn't be black if it wasn't a black hole there. And the orange donut around it, that is the light that's emitted by charged particles as they are moving around the magnetic fields that are around the black hole. So I'm going to show you what that looks like. So here's going to be a simulation. This is all the light emitted by the charged particles. Now, the gravity of the black hole is so large that the light is bent. So all those little charged particles, the light is being bent around the black hole. This is something predicted by Einstein, that light would be bent around massive objects in the universe, and this is called gravitational lensing. Thanks to gravitational lensing, we can see the ring around the black holes. But we don't see it as sharp as this. Our ring that we observed was kind of fuzzy. So we want to do a better job than this type of, than the fuzzy ring. So what we really want to do is we want to make a sharp image of the ring around the black hole. And the reason why we'd want to do that is because it tells us what the Schwarzschild radius is of the black hole, so that's very important. It tells us the mass of the black hole, it can tell us about the spin of the black hole, and it can also tell us about how the gas is moving into the black hole, which is something we don't understand and we don't know how to model in our theoretical simulations of black holes. However, to be able to get an image this sharp, we'd need to take an orange. It's like observing an orange on the moon with our eyes from Earth. okay? I can't see an orange on the moon, and we can't see it with our current telescopes. So how are we going to observe a ring that sharp in order to make these really important fundamental observations of black holes? Well, right now, to make the original fuzzy donut image, we're connecting up these radio telescopes. And that means that we have a telescope the size of the Earth. But to make a finer resolution image, we need more telescopes. And so the red points here show you the new telescopes that we would like to put in various locations around the world. They're on high altitude sites. It's going to be high frequency observation. We would like to observe 24/7 on these telescopes, and that will allow us to get the types of images that are much sharper than we can today. But we're still limited by the size of the Earth. Okay, we need to get bigger than the Earth. And so we now have a concept which we're going to be proposing to NASA in the next couple of years. We're currently developing the proposal for it, called the Event Horizon Explorer. And this is to put a radio telescope into space. And that means that we can make our current Earth-size radio telescope into one that's much bigger than the Earth. And however, the risk of this, the main risk that we need to retire, or the technology we need to advance, is the downlink speeds of data. So right now, to get the data analysed so that you can see a beautiful ring around a black hole, we have to print the data out onto hard drives and ship them like on airplanes and trucks back to Boston, where we analyse the data. It's very hard to do that from a satellite, and so we are working with companies who are also interested in doing high-speed laser downlinks. And the types of speeds we're talking about that we're going to require 256 gigabits per second. And so we're excited about this industry, public-private partnership that we're doing in order to be able to advance this technology. And this is one example of why astronomy is useful, is that the needs of astronomy can help advance technology, which can then be used in other areas, such as satellite constellations. Okay, one of the other main areas, aside from black holes, that we do at the Centre for Astrophysics is the search for life on other planets. We want to understand how do planetary systems form, how common are rocky planets, and then do any of the nearby habitable planets harbour life? And, we're very close to being able to do this. All we need to know is how much of the different molecules we have in the spectrum of extrasolar planets. So, for example, with Earth, we have oxygen, ozone, water, carbon dioxide, and methane. We don't have carbon monoxide. If we had an ocean loss M dwarf, so this is a planet that had oceans, but it's been lost due to heat, probably a hot atmosphere, it would have oxygen, ozone, water, O4, possibly no water. We could have a habitable carbon dioxide-rich planet, M dwarf, and that would have oxygen, ozone, water. It would have carbon dioxide, carbon monoxide, no methane. And then we could have a different type of planet called a desiccated carbon dioxide-rich planet. So desiccated means that it once had oceans, but volcanic activity have heated up its surface, and there's no longer any oceans. So you can have oxygen, ozone, carbon monoxide, carbon dioxide, but no water. So these are different types of planets that were once or still are habitable, and we would know which if we knew how much of each of these molecules we had. And we're close to doing this. This is a real observation of carbon dioxide in an extrasolar planet. This was the first one that was detected, and we had one of the 4 teams. We were leading one of the 4 teams that made these discoveries. Okay, and so we can also look at methane, water, and ozone in the infrared part of the spectrum. So that image the spectrum I just showed you was done by the James Webb Space Telescope. And so almost all of these other molecules can be done with the James Webb Space Telescope, except for oxygen. So you might notice oxygen is way down there in the blue, and that's in the visible part of the spectrum. The James Webb Space Telescope won't get there. James Webb is only an infrared telescope. The next generation to the James Webb Space Telescope is called the Nancy Grace Roman Telescope. That's also an infrared telescope, still won't detect the oxygen. And so we are building an instrument which aims on the Giant Magellan Telescope, which is to be built in Chile in early 2030s, which aims to detect oxygen on those extrasolar planets. Our instrument's called GCLEF, and it's specifically designed right where that oxygen is, and to be very, very sensitive to that part of the spectrum, so we can finally detect oxygen. We'll already have all the other molecules from the James Webb Space Telescope, and then in future the Nancy Grace Roman Telescope. So I just wanted to give you a teaser for the types of things that we're doing at the Centre for Astrophysics leading into our fireside chat discussion. And finally, I just want to briefly mention our solar program. As I said before, the Smithsonian Astrophysical Observatory started as a solar observatory. We're still doing solar studies. And this is the Parker Solar Probe. It goes really close to the sun, and there's tiny little thing sticking out at the top there. I don't know if the laser pointer works. A tiny little round thing sticking out on the side. That's called SWEEP. That's an instrument that we built, which is collecting the ionized particles coming out of the sun, and it's actually making measurements about the solar wind that impacts the communications on Earth, and it also impacts our other satellites. And it sometimes can affect communications. And speaking of the sun, I'd like to invite you to an event. We are running a virtual event, which is next Monday, March 18th, 1:30 p.m, where I'll be talking about and a couple of our solar astronomers will be talking about the sun, the solar eclipse, and the work we're doing at the Smithsonian. And this is in the lead up to the April 8th total solar eclipse that we will be able to observe here in the United States. So thank you.
Thanks, Lisa. I just love it when she says, we want to do better than creating that first image of the black hole that already won the Breakthrough Prize, which is a $3 million prize. And I wouldn't be surprised if Shep and his colleagues win the Nobel Prize for that image someday. But we want to do better. That's awesome. Today's topic is US leadership in space science. And a lot of space science is done from space. And that's where Dr. Smith, Randall Smith, comes in. Randall, tell us about your work with space telescopes, and why do we have to launch these telescopes into space? Why can't we just do it from the ground?
Well, we certainly would if we could, because doing any kind of astronomy from space, building anything in space like this, costs about 100 times more than doing it on the ground. And so if you can ever do it on the ground, we tend to do it that way. But there are certain things that you can only do from space. Usually because the Earth's atmosphere absorbs the light that we're trying to look at. Now, from our point of view, this is a good thing. You know, the ozone absorbs a lot of, for example, that very blue light, the ultraviolet light that would otherwise hit the Earth. There were speculations that the ozone hole was actually an astronomical conspiracy in order to allow UV observations from the ground. That was completely false. Although some astronomers did in fact set up UV telescopes in the South Pole to take advantage of the fact that you could get through there. So I'm serious, people really do try to do it from the ground if they can. But you really go into space because, for example, if you want to study X-rays, which is what I spend most of my career doing, you have to do it from space. It's the only way. X-rays don't make it through the Earth's atmosphere. You can't even use balloons because balloons can't go high enough in order to do this. You have to be doing it from orbit. There are other reasons why you might want to go to space. It's also much more stable up there, so you don't have things moving around. We're hoping to build, for example, a gravitational observatory, which will observe gravitational waves coming from, say, mergers of black holes. We have one of those here in the US, actually in Louisiana, and it's affected, amongst other things, by trucks driving down the highway. Just rattling the thing and then making vibrations. So there's other reasons to go into space, but those are the primary ones, is just the atmosphere.
Thank you. So we do have to send telescopes to space sometimes, but then you also heard about Dr. Keeley talk about the Event Horizon Telescope, which is the array of radio telescopes, and the Giant Magellan Telescope. That is an enormous project of combining 7 different mirrors that are 8 meters in diameter each to make a single 25-meter diameter mirror to be able to detect oxygen on other planets. These are big projects, these are expensive projects, and a lot of the funding comes from public support. Lisa, tell us the importance of public support for astronomy, especially in today's environment of constrained federal budgets.
Yeah, absolutely. So there's, people often ask us, what's the use of astronomy? So I'm going to give you some examples as to why astronomy is useful. We have a satellite that we just launched last year called Tempo, which is a pollution monitor. And so we're actually monitoring pollution hourly over the United States. And we're also a partner in a satellite that just launched 2 weeks ago called Methane Sat, also monitoring methane hourly over the United States. This is a finer resolution than we've ever been able to do in the past, 2 to 4 mile radius, so this is suburban resolution. How do we do this? Well, we're applying the knowledge that we developed over decades that we use to understand atmospheres of planets, any planet, extrasolar planets, planets in our solar system, our own Earth, as well as our space technology expertise, and then applying it for our own Earth. And what we'd love to have is a centre called the Centre for the Habitable Earth, where astronomers apply their expertise to Earth-based problems, because not only are we looking for habitable planets outside our solar system, we need to keep our own Earth habitable. Astronomy is also a gateway science for kids in STEM. So it's like a gateway drug, but healthier. Astronomy is one of the topics that really lights kids' eyes up. They get excited about it. What is a black hole? How many galaxies are in the universe? What is the universe expanding into? All these questions, it really sparks curiosity. And so you can use astronomy as a way to inspire kids into science. And I think you ask lots of scientists today, they'll say, oh, I love astronomy. I've always loved astronomy. Some of them will say, I wanted to be an astronomer. They didn't all become astronomers, they all end up doing other things, but it's a way to inspire kids into science. And so lots of astronomers, including the Smithsonian Astrophysical Observatory, are engaged in trying to encourage kids into science. And then there's technology transfer. So there's a lot of technology that has been transferred out of astronomy into other fields. X-ray astronomy is one example. So X-ray astronomers were building X-ray detectors many, many years ago, and they were then transferred into the medical field and used in medical X-rays. Then that technology actually advanced further than what we were doing in astronomy, and we are now, for our next large X-ray mission called LINX, going to be bringing back that technology from the medical industry back into astronomy. So there are these technology advances that are made through astronomy as well. We have a former postdoc from the Harvard Smithsonian who is now running a company which is using earbuds to measure your heart rate and the various rhythms in the different atria of the heart. And she's using the earbuds as a telescope and applying astronomy techniques to remove all the noise that your body makes from the data. Gets very, very clean data of your heart. And so now she's building up a big company.
Lisa, I'd like for you to touch upon a couple of things you alluded to there. One is I wanted you to talk about your Telescopes in School program. But before you do that, today's topic is U.S. leadership in space science. So tell us where U.S. is compared to the rest of the world, and why is it important that we continue to invest from that standpoint?
Yeah, so Australia is as I'm sure you're all aware, is a leader in science, both space science as well as ground-based astronomy. And we need to retain that leadership position. At the moment, our leadership in ground-based astronomy is at risk. And that's because the next generation of telescopes that we need to build, so we need to get telescopes that are 20 to 30 metre diameter in order to make the next best discoveries that we're going to make, such as oxygen on extrasolar planets. How did galaxies form in the early universe? How did the first stars form in the early universe? We need bigger ground-based telescopes to do that. We can't put a 20 or 30 metre mirror into space. And so right now, the Europeans are beating us to it because they joined together, many countries joined together, over 20 countries, into a consortium where they're putting together money at the treaty level, international treaty level, to build the European Extremely Large Telescope in Chile. It's almost done. 6 years and it'll be finished, and they're going to be observing on the sky, whereas our US-based telescopes, large telescopes, are falling behind. And so, this is my argument to, I was in DC on Friday visiting senators and House representatives to talk about this, the fact that US needs to get on board with this because we need to be there making those discoveries. But also, we need those telescopes to back up and support our space telescopes. Our ground telescopes find the targets for the space telescopes, and then when those space telescopes make discoveries, the ground-based telescopes then do a better job with the imaging and the spectroscopy that we need, because they're much bigger mirrors.
Thank you. Randall, tell us about public-private partnership and the importance of that. You worked with NASA for decades, and now NASA is pivoting a little more to encouraging private investments. Why is that important?
It's incredibly important because NASA does do flagship, huge, big missions. JWST costs $10 billion, and it is, in my opinion, worth every penny. It does great, amazing things. But NASA's approach to building things is conservative by definition. Failure is not an option, and that's true pretty much across the entire board. They've realized that they also need to be able to do things faster and cheaper. That there are times when perhaps you would be willing to take partial success or something not quite perfect, but at a much lower cost. And so if you saw recently, there was the Intuitive Machines landing on the moon. And I was amazed that they were able to do it. This is part of a new program that NASA has for what are called firm fixed price contracts. If those of you not in the aerospace world may not be familiar with that, in your world it might be just called a contract, where you get money and you deliver something. In the aerospace world, often, we'll just keep giving you money until it's done. It's a good business. NASA is trying to go to a firm fixed price contract to see if people can actually do this, to leverage this partnership with industry, and they're taking us up on it. And so that mission wasn't a total success, but it was something like $75 million, and it got nearly there. So for NASA to do that same mission probably would have been 5 to 10 times more expensive. They wouldn't have made the same mistakes that they made, but they would have spent a lot more money in order to avoid them. So now if maybe we can find the sweet spot, we might actually be able to do a lot more for a lot less. And that's the real hope with these partnerships.
Great. John, I guess we are going to go to audience questions soon, but let me ask one final question of our panelists today. And I want to go back to this question of, are we alone? So I want you guys to individually weigh in on, do you think there is life outside of Earth? And do you know if we'll get a definitive answer during our lifetimes? Start with you, Randall.
Okay, we actually debated this on the drive-in. I think that there is likely, and I think that we're probably most likely to find it in our lifetimes within the solar system. I think that if we continue to explore the outer planets, the moons of Jupiter and Saturn, we might well find some life in that area, is my guess. But I will now...
Yes, well, obviously we're building the GCLEF, this instrument to detect oxygen on extrasolar planets. I think we will detect life on other planets in our lifetime. I think it may be 10 or 15 years away because we need these next generation telescopes in order to do it. But it's not going to be intelligent life. It's likely to be bacteria. And because for the amount of time on our Earth over which there was bacteria in the oceans compared to the tiny amount of time in the Earth's history that humans have been here. If you were to just, draw from a lottery, okay, right now I'm going to look at the Earth over the whole Earth's history, you're just going to draw one snapshot. Most likely you'd see nothing or you'd see bacteria. And that's just the probability. So that's what I think we're going to discover. And sometimes, I have to say, sometimes I'm not convinced there is life on this planet, especially when I'm in DC.
All right, so as we go to audience questions, I'd request Joel to advance, just go through slide by slide. There are, I think, these. These are X-ray images from Chandra, which is another big NASA telescope that was launched and is maintained and operated by the Center for Astrophysics. These are the work that Dr. Smith does. And then we will go to our last slide, which is on leadership lessons that Lisa Cooley has prepared. John requested a set of leadership lesson bullet points given our theme for the year. And so here are her leadership lessons, and you can take a look at that as we will invite questions from you.
Well, everybody in the room knows that about the Big Bang Theory. And I'd like for each of you to answer a question for yourself about what happened just before the Big Bang, and why is there something instead of nothing?
Yeah, this is a question that my kids ask me, and they're very frustrated that I don't know the answer of what there was before the Big Bang. Astronomers, or in particular astrophysicists who do the mathematics of the Big Bang, say that it was basically there was space-time, but nothing much in that space-time except some tiny little ripples or a little inhomogeneity, so sometimes a little flicker. And then one of these then formed the universe. Astronomers, I think, some astronomers would believe that there are multiverses. I think a lot of astronomers would believe that there's multiverses. So you wouldn't just have one flicker that created the universe. There could be many of them that creates universes in space-time. We're not going to be able to see them or know that they're there because it's an additional dimension that we don't have, our brains wouldn't have access to, and we don't have access to here.
I think to save time, too, we'll have the other panelists maybe answer that question afterwards. We've never had that question before at Rotary. We may never have that question again at Rotary, but it's an excellent one. Jim, why don't you ask your question?
Deepak, you alluded to telescopes in schools, but you didn't get a chance to answer that. Could you say something about that, please?
Yes, absolutely. So we are aiming to put a telescope in every rural school in America. The reason for this is because the kids in the rural schools, they don't have access to the same types of summer schools, after-school programs, weekend programs, museums that the kids in the urban areas have access to, but they do have a beautiful night sky, and they can make the most of being out in the rural area with telescopes. This is a program I ran in Australia when I was director of my Centre of Excellence there. We put telescopes in many rural schools across Australia. We brought an astronomer out and a student and out to the schools. We ran an observing session. We trained the teacher in how to use the telescope, and then we provided materials on the website aligned with the curriculum which we developed with teachers so that the kids can do their telescopes both in the daytime with a solar filter so you can look at sunspots, or in the nighttime, and then it actually meets part of the curriculum for doing scientific experiments. And this is a great way to engage kids in science and technology. The modern telescopes by Celestron you can control with your mobile phone. All kids can actually log in with their phone, take photos, and these telescopes make beautiful, beautiful images.
Another question.
Thank you, John. I want to ask you a question about severe solar storms. I was reading an article a few months ago, and it was quite frightening, frankly. And apparently, over the past several hundred years, astronomers were able to detect severe solar storms, solar flares, and then something called a corona mass ejection. A couple of events, late 19th century, one in the early 20th century, well before the grid that we know it, much less satellites and internets. And they say one of these days, another one will hit. And the question to you would be, what do we think about one of those potential existential threats?
So I might let Randall handle that, because in the high energy division, there's a large solar group that is actually studying that exact thing.
And if people would like to Google and read more about this, there's one called the Carrington event, which you can Google and you'll find all about. And it was back in the days when it was all Morse code and telegraph machines. Today, you're absolutely right. If one hit us, we would need to be prepared for it. And as a matter of fact, a large coronal mass ejection did happen a few years ago. It just wasn't pointed at us. It missed us. It sort of went off at 90 degrees to where the Earth was at the time. And the reason I'm pointing that out is we now know a lot more about the sun and what's going on, and so we are now tracking these things at all times. And the sun, if the sun has a photon event, something that's pure radiation, that can do interesting things to the upper atmosphere, but it's not really going to cause huge death and destruction. One of these coronal mass ejections is the equivalent of several mountains of hot plasma hitting the Earth. That can cause very interesting effects, messing up satellites, causing problems with our power grid and all the rest of it. But we can see them coming now with the satellites that we're building. Actually, part of the team that we have at the CFA has people doing exactly that. So we'll get warning that it's happening. And there's a system set up to alert power grid producers and so on that solar storm coming, turn off everything. Which isn't to say it's going to be completely harmless. It would still be a very interesting event. But it would not be nearly as devastating as it might have been, say, 20 or 30 years ago.
And Randall, you're studying also anything else that might be heading in our direction, correct?
We are also studying, if you saw the movie Don't Look Up, as it turns out, if you read that, Leonardo DiCaprio at one point says, we need to contact the Minor Planet Center and tell them that there's an asteroid heading for the Earth. Well, guess where the Minor Planet Center happens to be located? It's part of the Smithsonian Astrophysical Observatory. We've had it there for many, many years, and they track all of the asteroids. And yes, there is a procedure for what to do in case an asteroid is heading towards Earth. I think it starts with telling Lisa.
I just want to add that we've got two junior astronomers who are studying the solar corona. One is going to be studying the eclipse on an aeroplane, so all the instruments on an aeroplane flying during the eclipse. And another one is actually going to be up in Alaska launching rockets during the solar maximum with instruments on those rockets.
So maybe a final question. One of the leadership lessons from Lisa and her panel, encourage a culture of innovation. Randall, you talked about the public-private partnership. And obviously, if you think about the private, you think about Elon Musk and SpaceX and what's going on there, rockets blowing up and then potentially taking off. Can you give us a little bit of an idea? What's it like for folks who are used to perfection to be working with folks that are actually excited about something that blows up because they can figure out how to solve the problem?
It is, you're absolutely right. SpaceX is an excellent example of that. It's a very driven environment. I've been told, I've got colleagues who work there. It's a lot like being in graduate school. You know, the expectation is that people are working through the night in order to solve problems and get things done, which is the kind of attitude that you need. And they've done things that you really only could do with private partnerships. For example, the truly impressive re-landing of their second stages, that probably cost $5 billion to develop, and I'm just wagging a guess there. That really, NASA probably couldn't have done that. They couldn't have justified it. But Elon thought, if we do it once and we figure out how to do this, it's going to save us money in the long run. And so he put the money into doing it. So there are completely new things coming out of this partnership of public money, because keep in mind, SpaceX did receive a lot of NASA money. That was part of the deal. But he has returned it with a lot of truly impressive rockets. And yes, there have been culture clashes, I will say, between the two styles. And that's one of the reasons why I think it's important to keep it in a separate box, because you couldn't do that within the NASA system. There are just too many people who are used to doing it the NASA way. But you can do it via a private partnership where they're still paying attention, but they're not, right up there that close.
And I should add that our Tempo satellite was launched on a SpaceX rocket, and it's piggybacking on an Intel satellite, communication satellite.
So Deepak, last question to you. We talk about where U.S. space leadership currently resides. What kind of a grade would you give us right now in the U.S. with regard to space leadership, and how do we improve it?
Well, there's a couple of layers of answers to that. One is when I see the leaders in U.S. leadership in space science, and by the way, I want to give a quick plug here to Sebastian Lupien and Mike Crenshaw. They're here from the Department of Physics and Astronomy right here at Georgia State University. And there's a group at the university studying space weather, which was the question about what happens when there's the next big solar storm. So when you talk to these people that are working on these hard problems and you see the progress they're making against insurmountable odds, like Lisa mentioned, you can't just do the science, you got to build the instruments in order to do the science. The Giant Magellan Telescope has earthquake constraints for that big a building, so they're learning a lot more about civil engineering that has never been done before. Trucks going on highways can affect these things. So when you talk to people doing these kinds of things, you're blown away with the caliber of people working on difficult problems and the caliber of technology that they're able to employ in solving these answers. The other side of the coin is, do we have all the investment we need to continue to lead? And there is some question mark there in terms of federal budget constraints, but that's where I think we're being creative with these public-private partnerships. So I'm optimistic. I'm really optimistic about the future.
Deepak, thank you. Randall, Lisa, for a wonderful presentation. You've been in the presence of some of the world's leading astrophysicists. You've heard some of the most significant developments, and you've seen an equation that nobody understands except these three people. Let's give them all a hand, and please come up after this.